Hello friends, in this video we are going to discuss about the doping of gallium arsenide. And gallium arsenide is a semiconductor, also is a binary semiconductor. Gallium arsenide, you can see there is gallium atom and arsenic atom. So it is an alloy of gallium and arsenic, so it is called alloy semiconductor. And this alloy semiconductor has type of materials, that's why they are called binary semiconductors. In these binary semiconductors, since there are two atoms, gallium and arsenic, we can see the 2D diagram, 2D atomic structure of gallium arsenide, which is given in this figure. So this is the 2D atomic structure of gallium arsenide, where the green color atom are these green color atoms are the arsenic atoms, and the red color atoms are the gallium atom. And from this structure we can see there are 5 electrons, 1, 3, 4, 5. These are the 5 electrons in the outermost orbit. Similarly, gallium is we can know that this gallium are group 3 element. Since they are group 3 element, so they will have 1, 2, 3 electrons at the outermost orbit. And this arsenic is a group 5 element. That's why they will have 5 electrons in the outermost orbit. And they are oriented in the gallium arsenide in this fashion, the given figure. So this is the 2D atomic structure of gallium arsenide. Now, if we want to dope this gallium arsenide, suppose we want to dope with group 3 elements. Suppose we want to dope with group 2 elements. If we dope group 2 elements such as beryllium, zinc, cadmium, etc., this group 3 element will enter the lattice of the gallium arsenide and they will act as an substitutional impurities. Impurities, when they enter into the gallium arsenide structure. That's why they will, that is the group 2 elements, that is beryllium, zinc, cadmium, will replace the group 3 element, that is gallium. That means group 2 elements will replace the gallium atoms inside the structure, and they will become, group 2 will become the acceptor impurities. That is, when we dope gallium arsenide with a group 2 elements, then this group 2 element will act as an accepted impurity for the gallium arsenide. Now let us suppose we have a group 2 element such as beryllium. Suppose this is a beryllium, and this beryllium, since it is a group 2 element, so it will have 2 electrons at the outermost orbit. Now suppose we have doped this gallium arsenide structure using this beryllium, and we know that the beryllium, which is a group 2 element, will replace the gallium atoms. Suppose this gallium atom has been replaced by the beryllium atom, and this gallium atom will have 3 electrons. So when it is replaced by a beryllium atom, then what will happen? There will be only 2 electrons, because beryllium will have 2 electrons and there will be a vacant space. There will be a vacant space in the lattice. That's why the beryllium or the group 2 elements, after replacing the gallium atom, will become acceptor impurities. That's why the gallium arsenide will become a p-type gallium arsenide after doping with elements. Now let us dope this gallium arsenide with group 6 elements. So if we dope with 6 elements such as group 6 elements such as selenium, tellurium, then these impurities will act as an substitutional impurities inside the gallium arsenide when we will dope the gallium arsenide, and they will replace the group 5 arsenic element. So this is the arsenic atoms, the green one. They will replace this green atom. So let us consider a group 6 element. So this is a group 6 element, and this group 6 element will have 6 electrons in the outermost orbit. So this is a group 6 element. Now if we dope this group 6 element inside the gallium arsenide, then this group 6 element will replace the arsenic atom, that is the green atoms. These are the arsenic atom. So they will be replaced by this group 6 element. Now when the arsenic atom will be replaced by the group 6 element, previously the arsenic atom was of 5 electrons in the outermost orbit. Now when it will be replaced by the group 6 element, it will have 6 electrons in the outermost orbit. So now we can see that 1 electron is in extra. Previously it was 5. Now we will get a 1 electron extra, which is bonded by a very small amount of energy. So we will have an extra electron. So it will act as an donor impurity. And the gallium arsenide will be N-type gallium arsenide after doping with group 6 element. So in this way we can dope the gallium arsenide by group 2 elements and group 6 elements. For the group 2 elements, the gallium arsenide will be converted into the p-type material, and if we dope with group 6 element, then it will be converted into the n-type gallium arsenide. So this is one process of doping the gallium arsenide to make p-type gallium arsenide and n-type gallium arsenide. There is another way we can make the p-type gallium arsenide and n-type gallium arsenide. Let us see the second process. In the second process, what we can do, suppose if we want to dope silicon, and we know that silicon is a group 4 element. Since silicon is a group 4 element, then the silicon atom will have 4 electrons in the outermost orbit. Now suppose we have a gallium arsenide semiconductor. We know the 2D atomic structure of gallium arsenide. So if we dope this gallium arsenide with silicon, that means we are doping gallium arsenide using silicon, and this silicon will have 4 electrons in the outermost orbit. So if this silicon replaces the 3 gallium, so we can write if the silicon atom replaces group 3 element in the gallium arsenide, that is gallium atom, then silicon will act as an donor impurity. And if this silicon atom replaces group 5 element, that is the arsenic atom inside the gallium arsenide, then silicon will act as an acceptor impurity. So in this way we can also dope the gallium arsenide using silicon to make the gallium arsenide p-type or n-type. So if the gallium arsenide is doped with a silicon and silicon is replacing the gallium atom, then we will have a n-type gallium arsenide. And if the silicon atom replaces the group 5 arsenic atom inside the gallium arsenide, then we will get a p-type gallium arsenide. And this type of impurities, that is silicon, which can act both as an p-type impurity or n-type impurity. This type of impurities are called amphoteric impurities. This type of impurities are called amphoteric impurities. Silicon will act as an amphoteric impurities, which can be a donor impurity as well as it can act as an acceptor impurity depending on which type of atom it is replacing. Similarly, we can also dope gallium arsenide with germanium, because germanium will also have 4 electrons in the outermost orbit, because germanium is a group 4 element. So it will also act, this germanium will also act as an amphoteric impurity. Experimentally, it is found that if we dope gallium arsenide with silicon, then this gallium arsenide will be converted into n-type gallium arsenide. That is, experimentally it is found that inside gallium arsenide, silicon is predominantly act as a donor, though the silicon has a capability of acting as a acceptor, but the acting as a donor impurity is predominant than the acceptor impurity action. Similarly, if a gallium arsenide is doped with germanium, then the gallium arsenide will become a p-type gallium arsenide. Though the germanium has a capability of replacing the donor impurities. But it is experimentally found that inside gallium arsenide, germanium is predominantly act as an acceptor. That's why the gallium arsenide will be converted into the p-type gallium arsenide. So this is all about the doping of gallium arsenide. We have discussed how gallium arsenide can be converted into n-type gallium arsenide and p-type gallium arsenide. There are different processes. So this is all about the doping procedure of gallium arsenide. Thank you.